Okay, so now let's discuss principal component analysis, which is a dimension reduction technique which uses the SVD that we covered earlier. It's called PCA. It's perhaps the most classic dimension reduction technique. So let me sort of write down the context here. I have my x1 through xn examples, data examples. Each of them are d-dimensional, right? Each of them is d-dimensional. So there are d features for each example. Now, the classic way of writing such data down is to actually write the examples as rows of the data matrix. So the data matrix is written as x1 is in row 1, x2 is in row 2, etc. So this is not quite consistent with what we have always done, but this is the way it's always done in this context. So I'm going to stick with this notation. So really I have d features going this way for each data point, right? x1 through xn. So there's the d features. So this is basically an n rows and d column matrix, n cross d matrix, right? So let me think of doing the SVD for this. Let me remind you what the SVD would be in this context. You're going to find, UIs and VIs as vectors such that this property holds that when VI goes through X, I get sigma I UI, and of course I'm going to write down the other side also, but we're not going to worry so much about that. When UI goes through X transpose, we get sigma I VI, and X can be written as summation I sigma I UI VI transpose, which can also be written as U D B transpose, right? And let's just remind ourselves of the dimensions of everything. Remember that so X is an n cross D matrix, so it basically operates on D cross 1 vectors VI and sends them into n cross 1 vectors UI. So look at what's happening. Basically, the UIs are you have as many dimensions in the UI as the number of examples, and you have as many dimensions in VI as the number of original features. And of course, the idea of principal component analysis is that you take a bunch of the dominant singular values. We'll assume as before that we'll order these things in this way, in decreasing order, and we'll stop somewhere, say at r hat, right? So we get, and we'll look at it basically how these singular values are decaying, and stop at some point based on criteria that we'll discuss in a little bit. So just to make sure, okay, so what is going on? So then if I stop at r hat, what have I done? I have actually said that each of these operations is a projection into a single number for each example, right? So UI is what? Is basically x1 multiplied by VI, and then x2 multiplied by VI. Remember, the x's are row vectors and VI are column vectors. These are the numbers that we have. So down to xn multiplied by VI. So these VIs are just taking linear. Each VI is taking a linear combination of the original features and coming up with a particular feature. And so what have I done? I have basically gone to equivalent an equivalent example, and let me call it now, since I was using the I notation for this, the jth example. Now, what have I done to the jth example? The jth example is coming somewhere here. It's xj star vi. Now, what I've done is the jth example corresponds to the jth entry of this UI, and that's going to be the ith entry of this jth guy. So let me just make sure I write it down properly. So basically what I'll have is the first entry is going to be xj times v1. The second entry is going to be xj times v2 up to however many you decide to take, xj times vr hat. So this is my let me change pen color. This is my dimension reduced example, and so basically the ith entry of this guy is the jth entry of the UI vector that you got by doing the projection onto VI, right? So basically, this guy, for example, is coming from U2, and it's the jth entry in U2. So when all is said and done, so what have I done? Oh, I forgot something. This is actually sigma I times UI, and this is actually sigma 2 times U2, right? Basically, when I operate the X matrix on V, I get sigma times U, right? So that's what it is. So basically, my let me write it down again. X hat J is sigma 1 times U1, the jth entry of that, sigma 2 times U2, jth entry. I'm running out of room. Sigma r hat times U r hat, jth entry. So so what have I done? Basically, what I did was a truncation of the SVD. So I did a truncation of the SVD to the R hat entries. So remember, I did this. I equals 1 to R hat sigma I UI VI transpose. And I can write it as, I'm going to label it UR hat, meaning I'm just taking R hat columns here. I'm just taking the R hat by R hat matrix of, diagonal matrix for the first R hat singular values. And similarly, I'm taking the first R hat columns of V, and of course it's a transpose here. And these guys represent the projections I'm taking in the original feature space, and these represent the results of the projection. So basically, my new data representation is x tilde, which is the truncated version of this thing, is going to be U R hat D R hat, and because I don't really necessarily need to keep track of what linear combinations I took of the features. I just need to say, okay, what came out when I did this, because these linear combinations are just basically these orthonormal directions that are well matched to the data. They might contain useful information, so I'm not going to throw them away, but this is my feature space, and I should really call these guys x tilde also, right? These guys x tilde in my notation. So x tilde is my my reduced dimension example, and so basically I have it's an n times r hat matrix. So just like the original data matrix was n times d, this one is n times r hat, and this is my this is the output of my PCA. So I should also note that the PCA is usually used on d-meaned data. So typical use is I have the x1 through xn, but I replace xi by xi minus the the empirical mean, which is just 1 over n summed over the examples, right? So each feature now has zero mean. So across the examples, once I do this. So once you do that, let's also realize that the PCA is related to the the SVD is related to the eigen decomposition of the A transpose A or A transpose matrix. So let's just look at what that means here. So if I look at X, the data matrix, remember I've d-mained it. It's n cross d. If I look at X transpose X, that's going to be d cross n cross d. And if I put a 1 over n here, sort of sort of an averaging interpretation. Let me just change pen color. What will I get? The ijth entry of this guy will be x. I'm going to switch notation. xki xkj summed over the examples. So I'm summing like that, 1 over n. And remember, I have removed the mean. So this is an example of basically it's the empirical covariance of the ith and jth features, right? Because remember, I and j are between 1 and d, right? That's what that guy is. And what is the so this is sort of the empirical covariance matrix. Let me call this C, because that's what we call the covariance matrix. C is d cross d. It's an empirical covariance matrix. So the SVD of, let me just normalize the X matrix also like this. SVD of this is a if that corresponds to singular value sigma I, then 1 over n X transpose X, which is corresponds to eigenvalues lambda I sigma I squared, right? So that's how we actually derived the SVD, by looking at a matrix like this, a non-negative definite matrix, and taking its eigen decomposition and then relating the eigen vectors to the singular vectors. So the eigenvalues of remember, this is the C that I have defined before. So the summation of the eigenvalues is actually equal to the trace of C, which is just the sum of the feature variances, sum of the diagonal entries of the diagonal entries. So basically the sum of the individual sort of variances of the features. So where should I truncate the SVD? Well, I could say, well, I want to explain 95% of the variances, right? So I could, for example, say choose the truncation point such that summation I equals 1 to r hat lambda I, which is the same as I equals 1 to r hat sigma I squared, is say 0.95 times the trace of C, right? you could think about it that way, and it's basically a sum of the variations in the feature. So the SVD explains in this case, or PCA in this case, PCA explains 95% of the feature variance. So it seems like a pretty sensible thing to do when you have this sort of unsupervised, want this unsupervised approach to dimensionality reduction. However, it's not necessarily always the best thing to do. It's pretty good when the number of examples is relatively small compared to the dimension, but we might be able to learn, patterns that are buried in some of the singular vectors we are throwing away in the truncation if you give me more data. And there are actually alternative techniques that might be better than these sort of partial SVDs, truncated SVDs in many situations. So it's a very valuable tool, but again, like any other tool, it has limitations that we should always be aware of. Okay, so I've talked a lot to give some insight into the PCA procedure, but let me summarize what you might typically do, right? What is to be done to do the PCA. So you're given a data matrix X, which is N cross D. So the examples are rows in the data matrix. You would typically d-mean first, so which means subtract the average of the rows from each row. And if you want to keep the sort of covariance and averaging interpretation, you may want to take an SVD of 1 over root n times x. You do an SVD for that, which is U d V transpose, and then you let me change pen color. Then you truncate based on some criterion. So and you would get U r hat d r hat as your new x tilde. And how would you truncate? You might truncate based on saying, I'm going to put the summation I equals 1 to r hat sigma I squared. Pick r hat to be the minimum such that this is greater than or equal to, say, some fraction. This could be 0.9, 0.95, 0.99, whatever it is, times the sum over the entire thing. Let me make it as general as I can. You will never have more than that many. The rank will never exceed the minimum of the number of examples on the dimension, and many of these singular values might actually be 0. But that's what you do, and that's basically say that I'll explain away. I'll explain some percentage of the covariance doing this. So that would be your feature vectors that you would, these are the examples. This will be sort of n cross r hat. These are the reduced dimension examples that you might use for downstream inference. And of course, let's not forget that the sum of the squares of all the singular values is simply the Frobenius norm squared of x. Right. So basically, I was looking at 1 over root nx, so I guess I should say Frobenius norm squared of the matrix without normalization divided by n, the way I have defined it out here, right? So in that context, that's the bar you're looking at, and you're looking at, do I get it to within 0.9 or 0.95 or 0.99 of this overall energy, which can be thought of as if I have gotten rid of the mean, it can be thought of as the overall variation or variance in the features.